Hello everyone, this is lecture 15, subspaces of vector spaces. So in this lecture, we're going to define subspace of a vector space, and later we're going to look at examples where we determine whether or not a given set of vector is a subspace of a vector space. Before we write down the definition of subspace of a vector space, just want to give you the definition of set, right? Even though in the last two lectures we talk about set of vectors, we haven't really defined set or gave down the definitions of set. So really a set is just a collection of objects, and the object here is called elements. So a set is a collection of objects called element. And to describe a set or we want to write down the information of a set, what we do is that you usually list a we usually describe a set by listing all or some of the element of the set and enclose them within the curly bracket. Right? So we describe a set by listing all or some of the elements of the set and enclose them within curly bracket. All right. So example, we can have a set of whole numbers. We can have a set of integers. We can have a set of, rational numbers, things like that. So the set of whole numbers. Right, so this is equal to 0, 1, 2, 3, so on and so forth, because this is the infinite sequence of number or the set of infinite sequence of numbers. We're just going to list out part of the set, right? Some of the element of the set. We can write this set of integers. It can be dot, 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 here, -3, -2, -1, 0, 1, 2, 3, things like that, so on and so forth. So this is also a set of infinite sequence of real numbers, but these are just integers, right? And we call this infinite set, because the element, we have infinitely many elements in the set. All right, so as you can also see here that the element of the set is written between or within the curly bracket. Right, so now we can write down the definitions of subspace of a vector space. So a subspace of a vector space V, right, is a subset H, I call that subset H of V that has the following three properties. The first property is that the zero vectors is in the subset H, right? So the zero vector is in H. Right. So we need this first properties or conditions to ensure that the subset H is not an empty set, right? So we want to say that H is not an empty set, right? So we always have to check the very first condition that this is the zero vector in the subset H or not. The second condition is that if U and V are in H, then U plus V is also in H. Right? And this particular conditions is to show that H is closed under vector additions. So H is closed under vector additions. And the last condition is that if U is in H and K is a real constant or scalar, then the product K times U is also in H. And they say that H is closed under scalar multiplications, is closed under scalar multiplications. All right. So again, the definition of a subspace of a vector space is that if you have a subset H of a vector space V, and you want to know if H is a subspace of capital V, then you need to check these three properties. The first one is that zero vectors is in the subset H to ensure that H is not an empty set. The second condition is that H has to be closed under vector additions, and the third condition is H is closed under scalar multiplications. If these three properties are satisfied, then you say the subset H is a vector space. Is a subspace of a vector space. All right, so let's do the following properties. Let's do the following example. All right, so in example 2, the set consisting of only the zero vector in the vector space V is a subset of V, right? Because you have a zero in the subset, or the zero vector in the subset, and you can perform the vector calculations where zero vector plus zero vector is also zero vector. So it's closed under vector additions. If you have any scalar and you multiply with the zero vector, it also gives you a zero vector. So the subset is closed under scalar multiplications. All right, so therefore you say that the zeros, the set consisting of only the zero vector is a subspace of the vector space V. All right, so the next example we have is that you have a set, or the subset H consists of the vector A, 0, B. So this is the column vector. For A and B are real numbers, so A and B can be anything on the real lines. Now we need to show that H is a subspace of R3, right? R3 because you have three components in the vector. Okay, and again, to show that a subset is a subspace of a vector space, you need to show three properties. That the subset has the zero vectors in it, right, to ensure that the subset is not an empty set. That it is closed under vector addition, and it is closed under scalar multiplications. So let's work out the details for this example 3. So first you need to show that the zero vectors is in H, right? So the zero vector is in H. Okay. Remember, A and B are real numbers. So A and B can be anything, right? So if you let A equal to 0 and B equal to 0, then you have the zero vector 0, 0, 0 is in H, right? So therefore, the zero vector, so the subset H satisfies the first condition that H is not an empty set, and that the zero vectors is in H. Now the second conditions close under vector additions. Right. Now suppose you have two vectors. Suppose we have two vectors, and two vectors I name it u and v, and u and v are of the form a1 0 b1, and instead of writing the column vectors, I'm going to write the transpose of the row vector. Save me a little bit of space of writing. All right, so you have vector u in this form. Why do I choose a1 and b1? Because I try to follow or mimic the form of the vectors in the set, right? So in this in this set, I have the vector of the form a0b, right? So I'm going to choose a1 and b1 related to vector u, and vector v is going to be of the form a2 0 b2. All right. Now I'm going to perform the vector addition and see what happened. So I want to see that where a1, b1, a2, b2 are just real numbers, right? Similar to the setup right here. So u plus v is equal to a1, 0, b1 plus, this is transpose because we have a column vector. B2 transpose. So it's going to be the same by adding the component y's. So a1 plus a2, comma 0 plus 0, comma b1 plus b2 transpose. All this is equal to a, comma 0, comma b transpose, where a is equal to a1, a2, and b is equal to b1, b2. And of course, a and b are real numbers. So it shows that, right, I obtain the form, the exact form from the subset that I have. So it shows that, so this implies that H is closed under vector additions. Now, for the last condition, you need to show that H is closed under scalar multiplications. So close under scalar multiplications. Right. Now, again, you're supposed to have, suppose we have a vector u of the form a1, 0, b1 transpose, right, where a1 and b1 are constant, real constant, right, in R. And k is also a real constant or a scalar. Then you have k times u to be equal to k times a1, 0, b1 transpose, or you just multiply k for every element in the vector. So you have k times a1, comma 0 times, comma k times b1 transpose, or this is equal to a0b transpose, where a equal to k times a1 and b is equal to k times b1. And a and b now are just real numbers. Okay, so this shows that the subset H is closed under scalar multiplications as well. So this shows that H is closed under scalar multiplications. All right, so because H satisfied the three conditions that the zero vector is in H, and H is closed under vector additions, and H is closed under scalar multiplication. So you can draw the conclusion that H is a subspace of R3. So you say that H is a subspace of R3. All right. So that's how you perform the problem, how to determine if a set is a subspace of a vector space or not. Right? Again, you need to check the three conditions that the zero vectors is in H, H is close in the vector, close in the vector addition, and H is close in the scalar multiplication. Now, in the next example, we have the following set. You have a column vector x comma x plus 1, so is what it, is defined, such that n a for x is all real numbers. And we want to know if H is a subspace of R2 or not. So in this case, what you can do is that you have the two-dimensional vector. So the first component is x, the second component is y, for y is equal to x plus 1. Right? So if you draw this particular line, y equal to x plus 1, then you see that this line will not go through the origins. So that means that 0 is not in the set. Since 0 is not in the set H, then you say it automatically can say that H is not a subspace of R2. Okay. So another way to look at that is that because X is all real numbers, you can let X equal to 0. And when X equal to 0, then you can see that 0, 0 is not in the set. Since the vector 0, 0 is not in the set H, then H is not a subspace of R2. Okay. To disprove a set is not a subspace, it's very simple, right? If it failed one of the three conditions of subspace of a vector space. Right? So in this case, the set given to you in example 4 does not satisfy the first conditions that 0, 0 is not in the set H. So therefore, H is not a subspace of R2. In the next example, you have two different vectors. The first vector is of the form x1, x2, and 1, for x1 and x2 are real numbers. And the second set is x1, comma x1 plus x3, comma x3. Right? And we want to know if this two subset, each subset is a subspace of R3 or not. So this is the graph for the first subset, and this is the graph for the second subset. So the graph of the first subset, right? So this is the three-dimensional case. You have three components, and you will see that this shaded plane, right, is above the origins. It will not go through the origin graphically. So therefore, the 0 vector is not in the set. And because the 0 vector is not in the set, you can say that the first part, so the set W is not a subspace of R3. Right. Another way to look at this problem is that you have this set, right, consists of all the vectors of the form x1, x2, comma 1, where x1 and x2 are real numbers. Then you can let x1 equal to 0, x2 equal to 0, and you can see that the 0 vectors is not in the set. So from part A, let x1 equal to 0 and x2 equal to 0, then we observe that the vector 0, 0 is not in a W, thus W is not a subspace of R3. All right. So That's how you disprove the first questions, right? For the second set, the second set is a set of that consists of vectors of the form x1, x1 plus 3, and x3, when x1 and x3 are real numbers. So we're going to do the same thing. We check that the zero vectors is in the set. The set is closed under vector additions, and the set is closed under scalar multiplications. If one of the conditions fail, then you can say that the set is not a subspace of the vector space. If you have three conditions are satisfied, then you say that the set is a subspace of the vector space. Okay, so part B here, right? You need first to show that the zero vectors is in the set. So you let x1 equal to 0 and x3 equal to 0. Then, right, so the vector x1, comma x1 plus x3, comma x3 equal to 0, comma 0 plus 0, comma 0 is actually a zero vector. So this zero vector is in W. Sorry, it's not H. Right. So the zero vectors is in the set, which is good. Right. Now move on to the second condition, that W needs to be closed under vector additions. Okay. So we say that suppose we have two vectors in W of the form. Right, so U is of the form U1, U1 plus U3, comma U3, and V is of the form V1, we V1 plus V3 and V3. Then you can perform vector additions. That is U plus V, or U1, comma U1 plus U3, comma U3, plus V1, comma V1 plus V3, comma V3. Then you just add the component wise together. All right, so U1 plus V1, then U1 plus U3 plus V1 plus V3, and U3 plus V3. So here's the conditions that we need to impose on this number. So I forgot to mention that U1, U3, V1, V3 are real numbers. Okay. Now, if you let U1 plus V1 to be X1 and U3 plus V3 to be X3, then you have that U1 plus V1 is X1 and U3 plus V3 is X3. So you obtain the following form of vector, that is X1, comma X1 plus X3, comma X3. Right, so this one is in W. Therefore, it just shows that the set is closed under vector additions. So this shows that W is closed under vector additions. Okay, now we move on to the last property, that is W needs to be closed under scalar multiplications. Now suppose we have U equal to U1, comma U1 plus U3, comma U3 in W, and some constant or scalar real numbers. Right. Then you do scalar multiplications. That is K times U equal to K times U1, comma U1 plus U3, comma U3, or this is equal to K times U1, comma K times U1 plus K times U3, comma K times U3. And if you let K times U1 to be X1, again, it's just real numbers, and K times U3 equal to X3, again, it's just some real numbers, then this is the sum here is equal to X1 plus X3. So therefore, this is still in W, right? So this implies that W is closed under scalar multiplications. And because of that, because W is satisfied these three conditions, 0 is in the set, the set is closed under vector addition, and the set is closed under scalar multiplications, then you say that W in this case is a subspace of R3. So you say that W is a subspace of R3. Okay. So hopefully you get the idea of how to perform this kind of determinations of if a set is a subspace of a vector space or not. Right. So far we just deal with set of vectors. Now we move on to another example where you have to deal with the set of 2x2 matrices. So in this example, W is the set of all 2x2 matrices of the form 0, A, B, 0. And we want to show that this set is actually a subspace of the vector space M 2x2. Okay, so this is a set of the 2x2 matrices of the form A0, B0. For A and B are real numbers. So for A and B are real numbers. All right. So three conditions that we need to check again. 0 is in, so in this case, the 0 matrix is in the set, and the set is closed under matrix additions, and the set is closed under scalar multiplications. So the first thing we need to check if the 0 matrix is in the set. So we let A equal to 0 and B equal to 0. Then you have the matrix of the form 0, A, B, 0 equal to 0, 0, 0, 0. So the 0 matrix is in the set W. Okay. Now the next conditions is close in the matrix addition. So we let or suppose U and V are in W, then my U plus V. Right. So U and V, let me be careful here. Then U and V are of the form. Right, so U, sin U is in W, so U has the form, let's say 0A1, B1, 0, and V equal to 0A2, B2, 0. Okay, where A1, A2, B1, B2 are real numbers. Okay. Then we have that we're going to perform the matrix addition. So U plus V is equal to 0, A1, B1, 0 plus 0, A2, B2, 0. And you just add the component wise of these two matrices. So 0 added with 0, you get 0. And A1 added with A2, you get A1 plus A2. And B1 plus B2, you get here B1 plus B2. Let me move this out of the way a little bit. And for the last component, 0 plus 0, you have 0. Right. Or this, I'm going to let A1 plus A2 to be A, right? And B1 plus B2 to be B. So the resulting matrix or the matrix of the sums going to have the form 0, A, B, 0, right? And this shows that the sum is also in the set W. So this shows that W is closed under matrix additions. Okay. And for the last conditions, you say that suppose U of is in, then U is of the form, let's say U equal to 0, A1, B1, 0, right? Where A1, B1 are real numbers. And consider K to be real numbers as well as real scalar. Then we perform the scalar multiplications, right? So K times U to be equal to K times 0, A1, B1, 0, right? Or this is equal to 0, K times A1, K times B1, 0. And if we let K times A1 to be A and K times B2 to be B, then this scalar multiple has the form 0, A, B, 0, and is also in W. So this implies that W is closed under scalar multiplications. Right. So for this given set, right, the set of 2 by 2 matrices of the form 0, A, B, 0, we show that the 0 vectors is in the set is closed under vector additions, and the set is closed under matrix multiplications. So therefore, you say that the set is a subspace of the vector space M22. So the set is a subspace of the vector space M22. All right. So that's it for me. In this lecture, we look at the concept of subspace of a vector space. Right? And to ensure a set is a subspace of a vector space, we need to check 3 conditions: that the 0 vectors is in the set is closed under vector additions, and the set is closed under scalar multiplications. That's it for me. Please let me know if you have any questions. Thank you.